So I'm going to kick us off this morning here with a quick update on Grace C, Grace Continuity, the next mission. Want to acknowledge the team of co-authors here, both from the US and Germany. Sebastian Fischer is the project manager on the German side, representing DLR, the German Space Agency. Of course, we have colleagues from GFZ on the SDS side joining us. We have a new project manager on the NASA side, on the JPL side. Bill Clipstein, many of you might know him, remember him from Grace Follow-On, where he played a vital role. He managed the LOI instrument for Grace Follow-On. So Bill is now the project manager here on the US side. Mike Gross has moved on to other jobs here at JPL. So let me just jump in and remind you here about the science goals and deliverables. By and large, it's very similar to Grace Follow-On the level 1 and level 2 side. Level 3 will continue providing the surface mass change data. Now, on the project ownership side, we also have responsibilities for delivering higher level data products, level 4. So think of like Greenland mass change, drought monitor, climate indicators in general. So these exist already, but not as part of the project side of Grace Follow-On, but these are now rolled in and more comprehensively under the umbrella of the project. In terms of contribution between the US and Germany, you see that broken out up here a little bit, who's responsible for what. The laser ranging interferometer, which is the prime ranging instrument on Grace C, will be contributed by both countries, the electronic side by the US and the optics side by Germany. Science data system remains kind of like we have it now. Mission ops, again, a GSOC supported by GFZ, and launch vehicle will be supported by Germany, meaning bought by Germany. Launch is planned for 28. So just a super high level status in this quick time here. We successfully passed the so-called critical design review earlier this year in May. Actually, the mission operations critical design review, which is held separately, is held this week at GSOC, and that's supported by other team members of us. David Weiss is there right now. That was going on today. They might have just wrapped up or about to be wrapped up for today. The primary spacecraft structures were delivered. I actually have a picture from this morning. I'll show you in a second that both these structures are in the clean room now. The accelerometers for both satellites were fully requalified and completed already last year. And we, on the science data system side, we continuously verify that all the requirements and deployment goals are met during the integration and testing. So the next big milestone is actually coming up in a couple of weeks, the so-called system integration review. Then we have this so-called key decision point D with NASA headquarters later this year in December, and we're on track for a launch in about 3 years. So I'm just going to show you a couple of pictures. These are just the platforms, and there's a lot going on. I don't have time to go in any details, but I just want to highlight that we won't have an MWI or KVR microwave ranging instrument on Grace C like we have on Grace Follow-On. It's just the laser, but we've added redundancy. So everywhere where you see a 2X here is added redundancy that we didn't necessarily have on Grace Follow-On on Grace. We did have GPS redundancy, but now it's both antennas are on top. We have 2 laser modules here. So you see the 2X there, optical bench electronics. So wherever we can have a backup, we added that for redundancy between the spacecraft to add robustness to the mission. And then I'm just going to have a bunch of pictures here that you see that it's actually being built. It's actually happening. This was earlier this year, or maybe already very late last year, the main panels. You can see the shape, the form. This has already progressed to being sort of semi-assembled here. Solar area fit check was done. You see some testbed computers, engineering models that are being simultaneously tested in the lab, vibed. Here you see the flight harness, the cabling on sort of a background, or sort of, well, not quite the flight. That's not the flight hardware that it's mounted to, right? But then these cables. This is the picture I mentioned from today. They're actually now on that table here in the background, and they're going to be integrated on the actual flight modules that are now in the high bay. So this picture is from this morning. This is what it looks like earlier today at Airbus in Friedrichshafen. So you can see that we have both satellites, and they're starting to be fully integrated. Cold gas feed module. So this is one of the elements here. You can see the pipe work. It's in final assembly. We'll then integrate it on these structures. Simultaneously, we're testing the hardware in the lab. This is a JPL here where the laser ranging processor and the scale factor unit are being integrated and tested. The bench optics and on the German side, everything is undergoing vibe testing, electrical testing, and so forth. And then just to wrap it up right here, real quick, the implementation is underway, progressing nicely. All the technical margins are very solid. On the right side, you see where we are, our requirements, and where the system performance is right now. So we're well below that, meeting all the level 1 high-level requirements. And I'll leave it at that, and we can revisit questions later. Thank you.
Thank you, Felix. Let's move on to the next presentation from Julia van der Toren. Julia, can you please share your screen?
Hi, yes. Can you see my screen?
Yep, we can.
Okay, perfect. So hello, everybody. My name is Julia. I am from the German Aerospace Center for Satellite Geodesy and Inertial Sensing that is located in Hanover in Germany. And today I will present to you MiniCAS. MiniCAS is a miniaturized constellation acquisition system. And so the success of gravity missions like RACE-FO, they critically depend on the two spacecraft to establish a stable laser link. Without it, no interferometric signal can be generated. Therefore, the so-called master spacecraft keeps its laser frequency fixed, while the transponder spacecraft sweeps its frequency. Simultaneously, both spacecraft carry out spatial scans using an already integrated steering mirror. This entire procedure takes about 9 hours and must be repeated. So after each measurement, the data must be stored, downloaded, and processed. So as a result, the full calibration takes about 2 entire days. While this concept is robust, the current approach relies on a time-consuming acquisition process, and errors in estimating the true line of sight and the frequency difference between the two lasers still remain and can pose challenges. Also, moreover, missions without an integrated steering mirror cannot conduct this type of procedure and rely on alternatives. And for this purpose, we propose MiniCAS, a dedicated hardware. MiniCAS is a modular system that consists out of an optical receiver paired with a dedicated light source called the emitter, and both systems are installed on both spacecrafts. So the emitter consists out of a light source that is now dedicated or located on spacecraft A and features a beam divergence that is large enough to cover the entire uncertainty cone. On the receiving end, the light enters spacecraft B through an aperture and pings on a lens system that then focuses the light onto a sensor. Now, as spacecraft A tilts, the beam will also tilt. However, due to the spherical wavefront and the large distances between the two spacecraft, the light does not show an angle at the receiving end. However, now spacecraft B will tilt, the light will enter spacecraft B through an angle. And this angle translates in an almost instantaneous information about the spacecraft attitude's orientation. So here you can see the module of MiniCAS. It has a size of 10 by 10 by 20 centimeters. It contains the receiver unit. This consists out of a baffle with an integrated lens system, an optical sensor, and a data processing unit. The baffle includes an aperture that directs the light onto a lens system. And for the lens system, we've conducted already simulations in order to identify which focal lengths to use for the lenses and also the distances between them in order to achieve the spot size that we want, as well as to meet the field of view and angular sensitivity requirements. For MiniCAS, we are using an indium gallium arsenide focal plane array, which is equipped with a CMOS-based readout. Well, positioned directly next to the receiver, we have our emitter. The emitter consists out of a laser module that has a size of 5 by 3 by 2 centimeters, so very compact, and is combined with the lens system as well. The entire emitter is specifically tailored to meet the requirements of our receiver, ensuring that both the wavelength of the laser as well as the output power are compatible with the sensitivity and the spectral response of our FPA. Hereby, a key design or consideration is that across varying distances between the two spacecrafts, the received optical power still or has to remain above a minimum threshold.
1 minute left.
Thank you. To list a few of the MiniCAS properties, a preliminary value of the field of view is about plus minus 5 milliradian. The angular accuracy is below 10 microradian, and we are aiming for a total mass of below 2 kilograms. Minigas is part of the DLR Admire project that includes 13 participating institutes from Germany. And for Minigas, we are targeting a TLR5 by the end of 2026. Beyond intersatellite laser interferometers, Minigas could also be applied in aircrafts, drones, or structural monitoring. Currently, we are investigating whether Minigas will also implement a star tracker mode that will be added after 2026 that potentially could be beneficial for great 3D scenarios as well. That's basically it from my side today. If you have more information or want to have more information, you can use this QR code that will send you to our homepage. Thank you very much.
Thank you very much, Julia. That was very interesting. I remind everyone that the presentations are uploaded, so feel free to download them and go through and reach out to the presenter. So up next, we have Linus Sihora from GFZ, who will update us on ESA Earth system models for future gravimetry missions.
Right.
Please, Linus.
Thanks very much. I hope you can hear me fine. I'll jump straight in. So I'll give you an update on the work we've done recently to update the ESA Earth System Model to version 3. Now, for a bit of context, the reason we're doing that is that in the preparation of future satellite missions, what is usually done is one performs end-to-end simulations. And for future missions, if you want to assess the target sensitivity, of course, you need certain input signals to detect. Hence why we're updating the ESA ESM, which is usually supplied as the input model to these simulations. I'll do this quite briefly because there's many layers. I'll go first through the layers that we're updating that have been in ESA ESM 2 before. For the atmosphere and ocean, this is probably the least surprising. We're using ECMWF's ERA5 reanalysis using surface pressure anomalies and density anomalies in the upper atmosphere. And in turn, using ERA5 as well to force the MPOM ocean simulation to extract bottom pressure. And in contrast to previous versions, this will be mass conserving for the ocean. In terms of hydrology, we're using TWS from a high-resolution OS list flood simulation performed by my colleague, Laura Jensen, which we're forcing consistently with ERA5 as well, and then extracting daily TWS output. Now, since there's not much time to go into comparison to what this looked like previously, I'll just point you to the recent publication by Laura, which you can find here. And move straight on to the ice layer, which we're developing in collaboration with Ingo Saskin and Bert Wouters from AVI and TU Delft, respectively. We're updating Greenland and Antarctica to include daily surface mass balance signals, as well as including a trend and acceleration signals for the ice dynamics. And for the glaciers, where we're also extending the domain of all of the glaciers, we're using daily surface mass balance, or depending on which glacier system, high-resolution elevation change trends. And in addition, even though it's a really small signal, we're also including some work from Moritz Langer, who calculated trends in the Arctic permafrost based on changes in latent heat. But those are tiny and mostly localized in northern Siberia. For the solid Earth, we're including the long-term trend from GIA, which we're simulating in-house with the viscoelastic lithosphere and mantle model, VILMA, done by my colleague Volker Klemann, where we include additionally or newly signals from low viscosity zones, and in addition also ice mass loading from the Little Ice Age. And as a difference to the previous version, we're not including any earthquakes, but instead work from Hugo Lecomte from the Finnish Geospatial Research Institute, we have a simulation of the Earth's core mass changes. We have a few new layers. First and foremost, I mentioned that the ocean layer is mass conserving now. So we have a dedicated mass conservation layer, which solves the sea level fingerprints as a solution to the elastic gravity rotation and deformation. And we're putting as input all of the non-mass conserving layers, so the atmosphere, hydrology, and ice. And this then combines, is solved in a sea level equation, giving us the sea level fingerprints. For the earthquakes, this is a bit of a larger collaboration. So we have an ensemble from Shinchan Han and Jean Zauber from Ohio State and Goddard, as well as work from Yoshi Tanaka from Tokyo and Carla Breitenberg from Trieste. And we include an ensemble of 15 events from various simulations. Right now, we're assessing how to best filter these earthquake signals to minimize Gibbs effects. And additionally, we plan to include 2 tsunami simulations for Tehuco and Sumatra. Lastly, we're also including a new layer, which includes ocean bottom pressure anomalies for the AMOC. Now, there's a dedicated publication if you want to read that. In addition, we're also including trends from erosion and marine deposition together with Niels Hovius from GFZ. Now, wrapping up real quick, ESA ESM will cover 2007 to 20. So it'll start right when ESA ESM 2 ends. It can be combined with the previous version. Same resolution in both space and time, identical file format. And you can expect to see this towards the end of the year, beginning of next year. And with that, I'll stop. Thank you.
Thank you very much, Linus. We can discuss more in the Q&A. We can move on to the next presenter, who will take us back to the LRI and for CubeSat platforms. Such presentation given by Joshua Reader.
Thank you. I hope you can hear and see everything all right.
Yes.
Yeah, great. So thanks for the introduction. As many of us are aware, most of these large-scale missions, GRACE follow-on type missions, are incredibly expensive. So these high costs do provide a high spatial resolution measurement via the use of the LRI, but they also limit the number of satellites which are able to be launched, and therefore also the temporal resolution that we can achieve. So for your reference, I'm just going to show the ground track coverage of the GRACE FO type mission, giving a monthly gravity field solution, which is unfortunately limited by the background modeling. And even in the case of MAGIC, we only obtain a solution every 5 days. So this leads to the question, how can we solve this without spending billions more euros to launch even more of these expensive satellites? So our current answer to this is the Sensoris project, which is a joint project between DLR, ZAM, and the Institute of Aerospace Technology in Bremen. The Sensoris mission proposes a high temporal resolution measurement using 16 cost-effective CubeSats, but compromises with low spatial resolution measurement as GNSS is used as the tracking method. This constellation gives a temporal resolution of 1 day, where simulations have shown that this should be sufficient to improve the limiting background models. In addition to the addition of the constellation of many CubeSats to the already planned GRACE-C and NGG-M missions allows complementary measurement and also provides opportunity for redundancy in the gravity field measurement. Looking to the long term, an increase in the temporal resolution could be performed by simply launching a larger number of CubeSats. Unfortunately, making the spatial resolution better is not so easy. Here we would need to implement some sort of inter-satellite link, and therefore included within Sensoris is a feasibility study for a compact LRI. So to highlight the challenge that we're facing, I'm sure you've probably seen this image before. This is the image of the GRACE FO spacecraft, which has an effective volume of about 4,800 CubeSat units. Our objective is to miniaturize the LRI system to fit into a CubeSat of approximately 16U, so 16 CubeSat units. In order to have a benefit from including an LRI system on a CubeSat, we've done some rough simulations and they've shown that a ranging performance of 1 micron per square root hertz or better should be sufficient. Comparatively, GRACE follow-on aimed for an order of magnitude better. Relaxing the performance requirement allows other technology to be explored as a solution. So for example, the use of a rubidium frequency reference by moving to a telecom wavelength system, for example, has advantages on the size, weight, and power requirements of the overall system. Here, in the top left here, I've included an image of a very compact rubidium frequency reference, which is smaller than 1 satellite unit, 1 CubeSat unit, and it allows a much more compact system, but further work is required currently to achieve a suitable laser frequency stability. Other suitable methods to counteract the highly varying thermal environment experienced in a CubeSat is also required. So using a low thermal expansion glass optical bench, such as in the bottom right here, may counteract some of these effects, but further simulations are required. Currently, we're developing concepts for a compact LRI system, with hopefully the first experimental work starting next year. Thanks for your attention. Please feel free to reach out to me on my email address, and I'm happy to answer any further questions as well later on.
Thank you very much, Joshua. It was a very interesting presentation. Let's move on, and the next discussion has to do a little bit with what we discussed yesterday with accessing sub-monthly high-frequency signals using a long-track observations from MAGIC, and Khosrow will give us the presentation from Colorado. Khosrow, the floor is yours.
I think you should go to the front. Sorry, give us a sec. We are having a bit of technical difficulty here.
Right.
Can you see my screen?
Yes, we can.
Perfect. Thank you. All right. Hello, everyone. My talk is about a long orbit analysis in terms of LGD that we developed before for GRACE and now extending it to the MAGIC constellation. All right. So for this study, I use a simulation of the MAGIC constellation with the polar pair at 488 kilometer altitude and an inclination of 89 degrees. And for the inclined pair, I use the 396 kilometer altitude and an inclination of 67 degrees. So one day ground track of MAGIC would look like this. So the blue is for the polar pair, gray C, and the red is the ground track of the inclined pair NGGM. So along orbit LGD observations are enabled by this transfer function, and the transfer function is just the admittance between the LGD and the range acceleration residuals. And the most important property of that admittance and transfer function is that it doesn't change with altitude, magnitude of the gravity vector of the gravity signal, eccentricity of the orbit, and so on and so forth. And it turns out that the transfer function also doesn't change with the inclination of the orbit. So in this plot here, you see the transfer function for the polar pair in blue and for the inclined pair in red. And you see that they agree very well with each other. Okay, now that the LGD and the transfer function applies to the inclined pair, you can obtain accurate gravity information from the inclined pair using the LGD approach. All right, so the LGD sensitivity kernel tells us how the mass changes on the Earth surface are causing the LGD at satellite altitude. So this map here shows the LGD sensitivity kernel for the polar pair. So these two green dots show the location of the gray sea above Sierra Nevada. So as expected, so the way that you should read this figure is like this. So how much one meter of surface mass in terms of equivalent water height would contribute to LGD at satellite altitude? So as expected, the largest contribution comes from masses right beneath the satellites, but we also have these two regions with opposite sensitivity, and they are the ones which cause the side lobes in the LGD analysis. So these two figures show the LGD kernel sensitivity for the inclined pair using over like an ascending and a descending arc, and they are very similar to the polar pair, except because of the inclination, the sensitivity, the direction of the sensitivity changes, which means that the NGGM would be sensitive also to mass changes which are not perfectly elongated in the north-south direction. So as we all know, one of the applications of the LGD approach is that is for observing rapid mass changes in the Earth system. So here in this slide, I would like to show an example of observing high frequency atmospheric gravity changes by MAGIC. So this is just the atmospheric changes in gravity in terms of LGD caused by atmosphere in just one day. So if you focus on Northern Europe, this is what the spatial sampling of gray sea, the polar pair would look like in Northern Europe and how it picks up those high frequency gravity changes in atmosphere. And this is what we will get from the NGGM, from the inclined pair, which you see is much better than gray sea because of the inclination. So the
1 minute left.
Sure. So if you have a mass change near the latitude of 70 degrees, it will be picked up much better with NGGM. And then if you put the two together, you will get the magic, which is just remarkable that we will get this sampling using just 1 day of data. And lastly, I would like to show a simulation of the 2004 Sumatra tsunami observation by MAGIC. So the polar pair, the gray sea, could see that tsunami 3 hours and 45 minutes and 5 hours and 20 minutes after the earthquake like this. So in these plots, the x-axis is LGD and the y-axis is latitude. So this is the observation that we are likely to get from gray sea if there's a large tsunami. But then if you add the inclined pair, it is very likely that we will get 2 more observations from this inclined pair from the NGGM. So 2 hours and 30 minutes after the earthquakes and 4 hours and 5 minutes after the earthquakes. And if you look at all these plots, you see that the largest LGD always correlates with it's above the leading edge of the tsunami. That's where we get the largest. But okay, so if we have just graceful and gray sea, this is what we get. But by adding NGGM, it just significantly increases the likelihood of tsunami observations, which is just remarkable. And that increased observation can be used for improved modeling of the earthquake and tsunami source. Thank you. That's it for me.
Thank you very much, Khosrow. So let's move on with the next presentation given by Ingo Saskin, who will discuss expectation of future gravimetric missions in cryospheric processes.
Yeah, hi. My name is Ingo Saskin. I'm from the Alfred Wegener Institute, Germany's Polar and Marine Sciences Institute in Bremerhaven. And the study I would like to report on, or parts of the study, was conducted for ESA project that is named up there. It's headed by Elias Daras. So what I would like to switch a little bit from the perspective of, so to say, the data generators, really to see what kind of impact future gravity missions could make in the cryospheric community in terms of detectability of cryospheric processes. So here you can see the spatial distribution of the uncertainty in polar projection. That gives you an impression sort of for the different missions, NGGM, gray sea, and then the constellation on the top left, MAGIC. On the bottom right, you can see the noise distribution for GRACE follow-on. This is for the Arctic. And for the Antarctic, the same noise fields are shown, except that on the bottom right, you can also see the uncertainty that comes from the surface mass balance, SMB. In short, we need this because we're trying to determine if we can, for the Arctic, in this example here, if we can determine melt events in Greenland with the new missions. And for Antarctica, we decided to look at the long-term trends, the discharge acceleration, which is estimated as the GRACE mass signal minus the surface mass balance signal. So let's start with the short-term variability in Greenland. On the left-hand side, you can see a time series of the seasonal mass balance anomaly for 2012, assuming a weekly retrieval period. And you can see the horizontal lines that are different colored to reflect the different noise levels of the missions. And then you see the true daily variations in surface mass balance driven mainly by melt. And you can see then the weekly averages. And you can, what is noticeable is that with the MAGIC weekly solution, it is possible to detect, for example, this double peak structure of the melt event in Greenland in 2012. Now, how would this spatially look like? This is the right-hand side of the presentation. You can see that this is sort of an image where the contours show you where the noise level, where the signal in 2012 would have exceeded the noise in the observations. So you can see that GRACE sea-like, because it has the polar orbit has a pretty good resolution on the northern of the part of the ice sheet. It would have picked this up. and NGDM in the southern part. And actually, if you combine both missions into the MAGIC mission, you would get a very good coverage of the melt events such as that. Switching to long-term processes now for Antarctica, as I mentioned, we estimate the discharge, ice dynamic discharge, as the long-term ice dynamic imbalance as the mass change minus the surface mass balance contribution. And on the left-hand side, you can again see can see a scenario. This is what the discharge acceleration is observed today from NCAR, and how this would sort of again exceed the threshold of the noise. So you can see that in West Antarctica, which is the fastest retreating area right now in Antarctica, you can see that we have a good detectability also along the Antarctic Peninsula, but also in parts of East Antarctica once we have MAGIC installed. So if we assume that we have a discharge acceleration...
1 minute left.
Yeah. If we assume that we have a similar acceleration in other coastal parts of Antarctica, similar to those observed today in West Antarctica, this is what you see on the right-hand side. There you would also see some things that could be detected with NGGM alone, not so much with GRACE. But as soon again as MAGIC comes in, we sort of cover all the critical areas also of East Antarctica, including, for example, the Totten Glacier system, which already shows today a strong mass imbalance, and is also in a similar geographic setting with a runaway grounding line and collapse-prone structure than West Antarctica. So this is what we got so far. For any more details, just contact me. Thanks.
Thank you very much, Ingo. And we can now move on to the last presentation of this morning's session, given by Luc Bousquet-Soler. And Luc will talk us about the energy imbalance picked up by spaceborne accelerometers.
Hello, do you hear me well?
Yes, we hear you well.
Good. So hello, everyone. My research is about simulating how we can reconstruct the Earth energy imbalance from accelerometers in low Earth orbit. So we know that climate change is driven by a set of complex nonlinear dynamics and feedback loops. But if we take the Earth and we imagine a control volume at the top of the atmosphere, the fact that it's warming up is essentially due to the fact that the energy going in is slightly larger than all the energy going out. And this imbalance is small, but not negligible, and indeed potentially measurable. Right now, all the estimations for this imbalance come from heat inventory analysis from different sources. And what we would like is to have an independent measurement from space that just takes into account the in and out flux of heat at the top of the atmosphere. We do have the series mission datasets that give us the long-wave and short-wave outward radiation as well as solar irradiance, but with current radiometers, uncertainties are just too large. So what we propose is, let's imagine we have one or a set of drag-free satellites in low Earth orbit, which are affected by both the Earth and the solar radiation pressures. With a precise accelerometer, we will measure the net effect of these two accelerations, which in the radial component already has embedded the effect of the outward Earth radiation and inward sun radiation. So an average of these measured radial accelerations would give a first-order estimate of the Earth energy imbalance. Now at JPL, they have been working, they have developed a simulator that takes the series data products as the simulated truth and reconstructs a set of Earth and solar radiation pressure acceleration time series for different orbit configurations. When I started my PhD this year, my first goal was to validate this simulator by what we call the internal and external validations, in which essentially I redid the steps that the simulator is doing and checked how the produced acceleration time series is matched. This is already the final result. The validation works, as we can see by the validation curves following exactly Monty's output. And also, well, note that in the shortwave acceleration here, the difference is slightly larger because this animation is slightly outdated. There was one last inconsistency that was not still included in these results. But well, this looks like a trivial step, but it actually was very useful to find and solve several different inconsistencies that were in the implementation, from the way we were averaging the shortwave map, taking into account the effects of meteorology and day-night evolution, to more significant issues. For instance, under certain numerical conditions, Monty was seeing fake radiation spikes that we tackle now. So the idea is that next generation of accelerometers can reconstruct these magnitudes of acceleration to the desired accuracy. And we think that this will allow for an independent and direct measurement of the Earth energy imbalance for the first time. Of course, what we're working on right now is assessing this capability when taking into account accelerometer errors, model errors, confounding effects, and even different satellite constellation architectures. So with that being said, I will be happy to answer your questions if anyone has some, and thank you very much for your attention.
Thank you, Luke. Thanks very much. And we can now head into the Q&A part of the session. There's a couple threads already on the chat. We can probably start from there, and feel free to raise your hand and if you have any question. There is a couple questions. We'll start with Jacob's question that has been answered about the non-graph forces, whether they have been considered. Then Linus, we had a few questions about the sedimentation layer that you mentioned. It's actually probably something pretty new that we are considering after like a couple decades of working into that. So there's a couple questions on that front. So you mentioned that you guys are going to probably include only the trend. Is it like a global map of trends of sediment transportation? Is there like any global sedimentation processing model to begin with?
No, this will not be based on dedicated models. So what we'll do is, here we're relying heavily on the expertise of Niels Hovius, who's a professor of geomorphology at GFZ, who's very interested in figuring out where the exact regions where we have marine deposition, because that depends very much on, for example, the region around the mouth of the river, and there's no real good global data set or simulation. So what we'll do is we'll take the best estimates that we have on where this deposition will take place and the magnitude of that trend, and then include sort of a simplified trend map to see if this is detectable with future missions, since it's right on the edge of what is possible now, right. I guess.
Yeah. Okay. And now that we still have you on the pod, there's some more questions coming from Ben regarding the earthquake layer. I can read them to you. So Ben asks if the point source or finite fault in your model.
So it's not really my model per se. So this is from, it depends a bit on which one you're talking about. We have an ensemble of 13 earthquakes, which come from Shinshanhan and Jin Zauber. And then there's the addition of the Tohoku earthquake, which comes from Yoshitanaka, and the Karaman Maras from Karla. And I'm not 100% sure of all of them, but I guess it's a mixture. I know it's a finite for the Tohoku at least. For the others, I'll have to check back with the actual modelers.
And are they co-seismic or post-seismic or both?
Both.
Thank you.
And of course, they'll somewhat artificially, they will not be in the exact time which they happen in sort of the real world, because we also have historic earthquakes. But we'll put them towards the beginning of the ESM timeframe, and then they'll have a post-seismic signal all the way to the end.
Okay, thank you, Linus. We can continue. It's Christian, and then it's Srinivas. Christian, please, go ahead.
I have a question for the Earth energy imbalance. And what I want to know is, do you have already thought about the thermal emissions of the satellite itself? And do you have a feeling for how accurate you have to know the surface properties?
Sorry, I think we had a bit of a technical issue. Can you please repeat the question?
Did you consider the temperature of the satellite itself, which will create a radiation pressure effect? And do you already have an idea about how accurate you need to know reflection properties of your surfaces?
These are indeed very good questions that we are trying to address right now. Yes.
Okay.
Thank you.
I was hoping you had some ideas because we hit the same problem with Grace follow-on for the density.
Right, I understand. We know that material properties will be a very limiting factor that we have to properly analyze. Thank you for your question.
Right, thank you. We can continue with Srinivas.
Hi, Athena. Hello, everyone. So actually, my glasses just went down. There we go. There seemed to be an ongoing conversation about the Earth system model. So in the interest of continuity, I can hold my question if you want to continue with the Earth system models questions in the chat. Otherwise, I can ask my question, whichever suits you.
Please continue.
Okay.
Your question.
All right. So JT can wait then. Hi, JT. So let's see. There were conversations about CubeSat configurations, and maybe I can ask it to the DLR group from Hanover since they have had 2 presentations on this. Are you also looking at the satellite topics, satellite fabrication or configuration or assurance topics in addition to miniaturizing the scientific instruments?
So you mean in that instance, what our platform may be and looking in that sort of direction as well?
Yes, thank you. Yes, that's better said. Yes, indeed. The platform and what it needs to be to accommodate and perform with the miniaturized instrument. Thank you. Yeah.
Yeah, so we're currently looking at several different platforms and also trying to get a better idea of actually what's available in the CubeSat regime. So 16 new CubeSats or larger CubeSats, there seems to be sort of a gray area there where some of them are not so readily available, and also obtaining data for some of these can be a bit tricky. So we are currently looking into the availability of different platforms and how that affects the LRI instrument as well, and what that means for example, the thermal environment. That's quite a big question as well for us. So.
Okay, thank you.
Thank you, Srinivas. Thank you, Joshua. We can continue with Felix.
Yeah, thanks. I just wanted to make a remark, actually, or a comment. It's not really a question, but I realized as we were going through the presentations, there were several references to NGGM and MAGIC, and we didn't really provide a context. Many people know about this, but I just wanted to say I had one blurb on my slides, but I didn't talk about it. So NGGM stands for Next Generation Gravity Mission. It is an ESA project, so out of Europe, overseen by ESA. Great C is a NASA, so US and DLR German joint venture, and MAGIC, the C for in MAGIC stands for the constellation. So it'd be when both missions are up simultaneously. I believe the timeline for ESA for NGGM is about 2032. We don't really have an update in the presentation. I don't know if anyone from ESA or from NGGM is on who can provide a little bit more updates, but just for context, that MAGIC is if both missions are flying concurrently. Grace C would be the polar orbit, and then NGGM, that inclined pair. Ingo had a couple of slides that spoke to that, but just wanted to provide that background since we didn't really touch on that today in the meeting. Is anyone on from ESA or NGGM that can provide an update where you might be at programmatically? I don't think so, but anyways, we can follow up with others later.
Yeah, Thank you, Felix. Thanks for the clarification and definitions. So let's move on with Steve.
Yeah, this is for Felix. I got on a little late this morning, so maybe you mentioned this, but the issues with Grace follow-on that led to going to coarser pointing and the fuel leaks, et cetera, are those being addressed for Grace C? I assume so.
Yes, of course they are. So Steve is referring to the fact that for Grace follow-on, we're letting the satellites point a little bit looser because we want to minimize the thrusting. There are small leaks at the thrusters, at the seals, we believe. The side effect of that, the collateral, is that we don't have the laser link. And of course, with Grace C, where we only have the laser, that's not a viable option. So on Grace C, the thrusters are entirely new and different. They are low shock thrusters also. That should mitigate some of the issues we had seen on Grace follow-on, where, right, we have very sensitive instruments. The laser is very sensitive. Software updates were made. So the entire AOC, oh sorry, the pipe work on Grace C will be different materials, and Airbus believes that that should all minimize and mitigate that issue that we saw on Grace follow-on, where we had these small fuel leaks. So I feel confident that that's been addressed. We've spent quite a bit of time on that to make sure we don't see that issue, because the mitigation we are running on Grace follow-on isn't really available to us. Does that answer your question, Steve? All right.
Yes, that's all good.
Thank you. Before we jump into Jada's question in the chat, Jakob, do you want to ask your questions? You froze. Can anyone hear Jakob?
I think he just
Jumped out.
he might have pushed the wrong button.
Do you hear me?
Yes.
Oh, yes, now we do.
Somehow I was interrupted. Sorry. Can I ask the question?
Please go ahead. Yes.
It's Felix. You mentioned the CDR. Was it just smooth, or was there some topics discussed more extensively, or is there anything more to report on that?
So the CDR was the critical design review earlier this year in May.
Yes.
No, it went very smoothly. I mean, there's no big concerns on the implementation side. Of course, a few things get a close look. The accelerometers, we had an issue on Grace follow-on, and we're flying the same accelerometers on Grace C. So obviously they've gotten a lot of scrutiny, and I think we understand the root cause pretty well and are confident that these instruments that we are now flying don't have that. Some of that was related to the instrument that's having the
You want to
issue
share
follow-on.
something about that?
What's that?
Do you want to share something about accelerometers at this point, like the understanding?
Well, I think it's so I can't really go into the super low details, not because it's secret or anything, but it's essentially believed to be a contamination issue inside the accelerometer, leading to incorrect measurements inside the core. And that can be traced all the way to a lot of rework that was done on that particular unit, right? It was opened up a lot because remember, there were issues with the gold wire that was then changed to a platinum wire. So as that rework was going on, right, like every time you open that up, very sensitive, it needs a very clean environment. There is an issue or a potential for contamination. So conversely, the units we were flying on Grace C had no rework done, and right, and there's also in the data, actually, right, hindsight is 2020. In the testing data, there are signs. I don't know what exactly was measured. Some capacitance, I want to say, that in hindsight, would have revealed that there is a difference with this particular accelerometer on Grace follow-on, where we have an issue that could have led you to, suspect that something is not quite right. So knowing that, the test program has, or the checkout program has been expanded for these units for Grace C, and everything has gotten a very close look. So I think I feel confident on that front that we won't have that issue on Grace C.
Thank you very much.
And I hope I don't forget to these words in a few years, but I
This meeting is recorded.
I understand. So yes.
Yeah. So also like Felix, Christian I guess not on behalf, but like reported on the NGGM status that they're waiting for some deliberation from ESA by the end of November. That's the information we have. And going back to JD, JD, I think there is a discussion in the thread. Is your question answered regarding groundwater?
Yeah, I think we're good. I really like the work that Linus presented. It's really cool to see that simulation and everything put together globally. So I was just asking about groundwater. I guess in the land surface or in hydrology, a lot of the long period signals tend to be in the subsurface in groundwater. So if there's a global mass budget closure, then it's really important to get groundwater right, which is hard to do for these models. So thank you.
Thanks, JD. It's a great introduction for our next session,
Yeah.
which will be on hydrology and water resources. We have almost 10 minutes, 9 minutes. Is there like any other question from anyone here? No?
Well, we could wonder about any go backs from yesterday also. I think we answered everything, but if anyone woke up last night with some burning question that wasn't answered, that would be the time to revisit that.
Right. It does not appear to be the case. So
Yeah.
we have like 8 minutes, so we can get a quick break and meet back here at 8 a.m. California time. That will be 5 p.m. German time, from what I see there.
Yeah,
So
5 p.m. on the
Yep.
German
Cool.
time. That's right. Yeah.
All right, everyone.
Take
See
a
you in a
quick
bit.
break. Actually, just for this case, I did prepare a little filler here. If we can, let's see if I can pull that up just for kicks, because that's also going to come up, I believe. Okay, so hold on. I've got a Mentimeter question for you that you can answer in the chat. So this is about how people are using AI in their work, and if you're doing that. So let's see. With this link that I sent, oops, am I sharing my screen?
Yes, you are.
I don't know what I'm doing here though. That kind of was weird. Okay. Let's see. Get some answers popping in. So just be curious. I think we're gonna have there's at least 1 or 2 presentations that will touch on AI in the next sessions. Of course, it's a very ubiquitous tool these days. Here at JPL and our group, we have a lot of discussions on how to use it, how to implement it in our work. It's, of course, a big playground, but we're also trying to see how to make it productive. A lot of people are using it for coding tasks. I think that's playing out here as well. That's interesting. Yeah, just kind of curious how it's starting to pop up in our regular workflows and in the tools we use. So I think you can vote multiple times.
Can I ask you something, Vince? When you say for coding task, you say because I mean, it's like for when I have a program to write to be helped, or for doing research within the coding, because complex research tasks, I mean, it could be like if you want to find, when a behavior said, you can just like, unsupervised and learning or things like that. Do you define that a coding task?
Yeah, it's kind of open, right? So it's whatever, some people have it as really for code completion ingrained in their IDE that they're using. Others are using it just kind of offline as, ask ChatGPT or Gemini or whatever to write them a script. I've used it that way. It's pretty impressive to just retrieve, some groundwater data that had maybe a weird interface, write me a little shell script. So sometimes that works, sometimes that doesn't. I think because I have a free account, we've reached the limit of the votes here. But nonetheless, this is interesting. I mean, it's kind of what I expected. A lot of use. So it's going to be interesting. I think we're going to see a lot of that being used going forward in our work and ever more ingrained in our workflows.